Thanks for tuning in to Luxoft's newest issue of TechSpark, the Data Issue. With our TechSpark podcast series, you can listen to great insights no matter where you are. Your time is precious to us, so whether you're on the way to work or have errands to run, tune in to keep up on the emerging technologies in the world of financial services today. A Hacker's Guide to Artificial Neural Networks. Introduction. In recent years, inspired by their biological counterparts and the relatively recent increase in computing power, artificial neural networks have taken center stage in an increasing number of industries. The increase in data collection has raised our desire to uncover relationships within our networks that could help in the exploitation of new opportunities. Neural networks give us the ability to construct extremely complex models from this data and provide a mechanism to predict future events. Artificial neural networks allow us to create an internal representation or model of a solution using a set of input scenarios and expected outcomes. Instead of the hard work of creating a complex model using multiple input and output parameters, artificial neural networks construct a model by a process of learning, which tunes the model to the expected outcomes we know about in much the same way a biological brain would. There are, of course, many differences between the biological counterpart and artificial networks. One of which is the dynamic nature of biological networks. Connections are constantly being created and destroyed. Currently, they only replicate the very basic structure of their biological counterparts, but are coming up with extremely interesting results. Neural networks can solve many problems that can also be solved by other existing algorithms, decision trees, k-nearest neighbor, etc. But where they become particularly powerful in model creation is when there is a large number of inputs with a large number of predictions. So why use neural networks at all? In a world of ever-expanding information, where companies have large sets of structured and unstructured data, often held in vast enterprise stores, they often have an enormous task to uncover relationships hidden within. Finding relationships between datasets can be achieved through statistical analysis and often brute force searching. But the resultant model is then only as good as the creator's model. Neural networks will allow us to capture and model undefined relationships on our behalf. If we can train the network to a tolerable threshold, then it might be a suitable model for predicting future results given new input data. There are plenty of frameworks available, most of which require a good understanding of neural networks at a high level, with multiple levels of configuration to suit your data. However, we will chart our journey through the building of a rudimentary neural network to uncover its challenges and rewards. Building the framework. To better understand how a neural network works, we decided to build one from scratch to understand how it fitted together and what impact different data had on outcomes and performance. By trying out a real set of sample data, we wanted to understand the entire process, from manipulation of input data and the tuning of the weights to the understanding of the results. Our goal was to construct a system that would discover the complexities hidden within our data without having to understand them or discover them ourselves. We have data that, given an observed set of inputs, sees the model change to match the given set of outputs. We therefore wanted to create a system that will construct a model representation of our data, however complex, so that we can use it in the future with new data to predict an outcome that would have otherwise been very difficult to have achieved. Our system is a supervised system, which means we provide the inputs and the expected outputs. Understanding the framework. Our first task was to discover what the standard neural network framework would need to contain. Each input corresponds with a unique parameter in our data and is represented by a single input neuron with the input layer. Each output in turn corresponds with a neuron in the output layer and represents an expected result given the input data. In between is a model representation of our specific data set and the complex relationships within. Framework components. At a basic level, the system contains layers and neurons. Neurons, objects that associate inputs and output connections and house a mathematical function. Layers, a set of neurons. Connections, inbound and outbound weightings. The mathematical activation functions that are invoked when the system is in training mode come in many different guises, each useful in their own way, depending on the data, as we see later. Rectified linear unit, ReLU. Hyperbolic tan, linear. Binary step, softmax. There is always on a single input layer and output layer at least one hidden layer, housed between the input and output layers. Our build started by first constructing the framework to hold the multiple layers of neurons. The input layers designed to take on the rows of input data, the output layer for the expected data, and a system to insert multiple hidden layers in between. The number of hidden layers and their number of neurons will be determined later. Each neuron within the hidden and output layers has a concept of a weighted connection, which houses the weightings between neuron and the next. Training the networks using our dataset requires tweaking each weighting within the network, so that whenever we introduce a new set of input values, the resultant outputs will be as we expect. Training the model can be done from left to right, or from the input layer through the hidden layers to the output layers by tweaking the weightings incrementally each iteration. This mechanism is called feed-forward. However, it is very slow and prone to either not converging or, at the very least, proving very expensive computationally. Examples include extreme learning machines where parameters and weights of hidden neurons do not need to be tuned, but instead randomly assigned. Backpropagation, or backpropagation of errors, was introduced, which using various activation functions works from the outer layer back to the input layer. Making use of backpropagation hugely increases the chances of convergence. Whilst there are many activation functions, we choose to build only a few, which we mention above. In our implementation, we decided all neurons within a specific layer would have the same activation function, and that each layer could have different activation functions. Activation functions simply sum up all the input weights, adds a bias, and then determines how the neurons should fire. The weights on these neurons are what encode the knowledge or model of the system. Preparing the data. Our dataset contained values where a combination of input values resulted in an expected category. In this example, we found that the best results were attained by ensuring that the output values or expected results were binary, so either 0 or 1. It was therefore very easy to identify if the values were near to 0 or to 1. We found that if a single output value was used that had a range from 0 to 1, then it was often difficult to interpret the results when a prediction was attained. For final validation of the model, it is important to take out a random set of training data for use as validation. Learning strategies. We decided on supervised learning because we had expected results with our input values. It also appeared to be the easiest way to see if our framework was doing its job correctly. Our framework was to be tested using two different sets of data. The first set was very simple, with two inputs and a single output, and would emulate the exclusive OR, XOR gate. The two inputs are either 0 or 1. However, the result is a 1 if the input values are not the same as each other, and 0 if they are. Before we could start training our network, we had to choose which activation function we were going to use, as initially we wanted to restrict it to just 1 for all layers. Our initial choice was the sigmoid function, figure 3, which has a gradient for most values other than at the tails, where the learning rate decreases as the derivative tends to 0 asymptote. This issue is known as the vanishing gradient problem and can cause the learning rate of the network to greatly slow if not stall entirely. This is important in the backpropagation to tune or tweak the weightings. However, in our XOR example, we found that it didn't perform as well as we had expected. If the values were close to 0 or 1, then they were less likely to be changed by the activation function, and convergence was slow, so we tried a different one. Our next choice was rectified linear unit, ReLU. See Figure 4, page 35. Introducing ReLU, while still slower than we hoped, increased the convergence rate and allowed us to train our network faster, and therefore allowed us to work with larger amounts of data. Our learning experience. By using the XOR function, we were able to construct a dataset. This was also the case for the unit circle example, and both XOR and unit circle were improved by the ReLU activation function. In the two examples above, our data was created using the two functions. We then moved on to a simple categorization example, where our dataset consisted of approximately 10 inputs and a single categorization or output. We again used the sigmoid function, but found that the training was outperformed by using ReLU. Our datasets were relatively small. If they increased into very large datasets, then training the network would take longer to perform, and there may be a very real chance training might not complete in a manageable time. It is at this point that we chose the use of stochastic gradient descent, which employs randomization of many datasets to achieve training success. This is a popular method for large datasets and large model size, and has become industry standard. Finally, we also had to work out what our learning rate would be. This is the rate to which we climb or fall down the gradient. If the learning rate is small, then the training will be more reliable, but it may take a long time to converge. However, if the learning rate is too high, then convergence may not happen. We therefore started very low, 0.0001, and slowly increased it to tune our dataset. The eventual range was between 0.0001 and 0.01. The last thing to think about is the number of layers. This can depend on the complexity of the relationships within the data. In our case, we decided on a single hidden layer, but after starting with 2 neurons, however, we did experiment with additional neurons and layers. We found that the more neurons and layers added, the more reliable the learning. Although there is a cost in computational time, deep learning employs the use of many hidden layers, and for very complicated models, this may be necessary. Trained network. Once our network was trained using our dataset, our network was ready to be used for new predictions. The XOR function is not a good example because the entire combination of inputs was used to train the network, so there was no new data to predict. For the categorization example, we held back some of the input data and their expected results to use a way of measuring the trained network prediction capability with what we know are expected results. Our results were within tolerance when it came to predicting values that were inside of the training set inputs, but as we strayed outside of these values, we found that the chances of the prediction being wrong increased. Our second data set represented requests for quotation, RFQs, and their eventual outcome. The inputs include data, time, traded price, quantity, buy or sell, product, outcome, and client. The goal was to predict the likelihood of a customer successfully executing a specific product. Initially, date and time were taken out of the dataset, but in possible subsequent examples, they could be used to determine a day of the week to be used to narrow the prediction criteria. Once the system was trained, we were able to provide it with new trades and predict the likelihood, as a percentage, of a successful outcome. Resultant information of this kind is useful to add to the decision-making of an organization when trades are being done in real time. Do we need to understand the model anymore? Up until this point, we have been very keen to understand the world around us by modeling it in as much detail as possible. For simple models that have few parameters with defined intervals, this is achievable. But as the number of parameters starts to increase, the complexity can increase exponentially. In the past, the model was the most important, with the data as a poorer cousin. However, in the modern world, data is so vast that the models can be extremely complex to create and understand. Artificial neural networks give us the chance to build models that are immensely complex without having to understand them. Where do artificial neural networks fit in the financial landscape? Most banks collect huge amounts of data and are now placing them in large data lakes. This data is sometimes well understood, but often, with any large repository of unrelated data, there is the opportunity to gather it all into a single learning system and see if relationships can be uncovered. Artificial neural networks allow us to tackle this problem by processing large amounts of data and data types, resulting in predictions that otherwise could not be achieved in the same time frame. The models can be used to predict financially driven models. For example, the likelihood of success of a trade given the customer. Any predictive system is an important tool in an investment bank, and used in concert with existing tools, allows insights that may never have been conceived without the intervention of AI. Skepticism and criticism of neural networks. There is skepticism when it comes to artificial neural networks, and this can often come from trying to create predictions from datasets that sit outside of the training datasets. The prediction can prove to be very inaccurate, as the model is very specific to the dataset. Understanding your requirements is therefore paramount when employing an artificial neural network, as it is not a panacea. Understanding the model weakness is also important if model reliance is high.